Hi, it's Gate. Welcome to eSchool platform. I'm called Remy and I will be your maths and further maths teacher. I've been teaching for 7 years in the same field, and for those of you who know me very well, I am also called the inducer. We are going to be solving past GCE questions and mocks in mathematics and additional maths for the O-level students, and in pure maths, math mechanics, math statistics, further pure, and further math mechanics. That's for the A-level students. Stuck anywhere, feel free to leave your worries in comments. I will personally answer them. It's Gates. Let's kick off.
Hello everyone, welcome back to eSchool platform. So I'll be presenting you a solution to June 2022 Pure Maths with Mechanics Paper 3 for the A-level students. So to begin with, we'll start with question 1. In question 1, where we are to get the magnitude of the momentum, so we're given the position vector at time t, and we are given the mass, which is 3 kilograms. So when t equals to power 8, the first task is to get the momentum of the magnitude of the momentum of the particle. So in that case, we remind ourselves that the momentum first we have as mv, yeah. So we derive therefore the velocity component from the r on dt based on the position vector. As you can see, v now becomes the r on dt. So as value, we have 6 cos 2t by basic differentiation, I minus 8 sine 2t j meters per second. So replacing t as pi on 8 on the v, we have as value 3 root 2i minus 4 root 2 meters per second. So therefore, the momentum first, which should therefore be mv, the mass which is 3. So simplifying, we have 9 root 2i minus 12 root 2j kilogram meters per second. So therefore, the magnitude now becomes the square roots of its values. We have the 9 root 2i plus into negative 12 root 2 other square, and then give us as 9 root 6 kilogram meters per second. So in B, we have to get the force acting on the particle. The force which is given as ma, that's times the acceleration vector. So in that case, we need to know the acceleration vector since we already have the mass. So the acceleration vector, which is given as dv on dt, that's change in v on change in t. So having the acceleration, we have negative 12 sine 2ti plus negative 16 cos 2t j meters per square second. So therefore, using t as per 8, we have as value negative 6 root 2i minus 8 root 2j meter per square second. So therefore, the mass, which is 3, we can directly have the force acting on the particle as 3 root 6 into negative 2i minus 8 root 2j. Since force is a vector quantity, we remind to add the newtons, as you can see. Therefore, give us a force as this unit, newton. In C, the last question is to get the power. So to get the power developed by the particle, since power is a scalar quantity, therefore our power will be as force the dot the velocity vector. So we just made the replacement since we have solved to raise the velocity vector in terms of t, and then we got the force in terms of t. We can then have as power the dot product of f and v. So when we dot our two vectors, we have as value negative 108 plus 192, which will give us 84 84 watt. Remind ourselves that dotting two vectors, we dot only their unique i's along with the i's, and then we take the j's together with the j's to have a complete scale values of p. So that gives us all for question 1. In question 2, we have Newton's second law, where we have two particles P and Q, and P is on an inclined plane, and then Q hangs vertically with an elastic string passing over a pulley, and then where our pulley is smooth. So again, we have the tension. They share the same tensions since they all have the same elastic string. And again, we have the movement of acceleration on P, as you can see, acting upward, and on Q we have it downward, since the weight on Q is more heavier than the weight on P. And then again, we have the normal reaction on P, and since our plane has friction here, mu, so in that case we have it on the plane directly beside P. So resolving the weight at P, we have 10g cos 30 degrees, and we have 10g sine 30 degrees. So on the question task, we get the acceleration of P. So to get the acceleration of P, we first need to resolve the forces. So the sum of F external force is balanced by MA. So in that case, we can see at Q, 20g minus T equals to 20. Give us as equation 1. And then at P, we can directly resolve perpendicular to the plane. You can see it's R equals to 10g cos 30 degrees as equation 2. So using equation 2, we can directly have the normal reaction at P, which is 503 g Newton. So again, when we solve equation 1 plus equation 2, we can be able to output the acceleration acting on the particle P. So we then have 1/3 into 15 minus 2 √3 meters per square second. We remind ourselves, since the particles are connected, they both share the same tensions and the same accelerations. So in that case, the acceleration acting on P, we have on the slide as this value. Now, using equation 1, we can now have the tension force, which will be equation tax on the string, and the tension force now give us 20 into 5 plus 2 √3 on 3 newtons for the tension force. Now, in that case, in C, we have to get the magnitude of the force exerted by the string on the pulley. We remind ourselves that at the pulley, we have as a derived force 2t cos alpha on 2, where this alpha is the angle at the pulley. So if we come back to our pulley system that we drew, we see that at the pulley, with this the pulley here, the angle here we have it at which is complete 90 degrees. Then here, if here is 30 degrees, it means here our alpha becomes 60 degrees, as you can see, since the total since at right angle. So we take 90 minus 30 degrees, and then we have at the pulley derived angle 60 degrees. So our alpha drops as 60 degrees. So that's the alpha we're going to use to solve the force, coming back to the force at the pulley. So we're placing 60 degrees here on alpha. We can then have 30 degrees, as you can see. So finally, using the tension force solved previously, give us the force acting at the pulley. So therefore, the magnitude give us the value in Newton. In sub 2, we then have circular motion. In circular motion, we are asked to get the angular displacement. We have a particle which moves in a circle of radius 2 meters, and we have the acceleration as its value 8 pi on 82 meter per square second. So remind ourselves that the acceleration, which is radial, we have r omega square. So r omega square there, given the radius as 2 meters, you can be able to come out with the angular velocity. So with the angular velocity, we can then put that, but our omega is theta on t, so replacing our omega, and take note that our theta is the angular displacement of the particle as resulting to the circular motion, and t is our time in seconds. So replacing our calculated value omega, we can then have our angular displacement 2 pi on 3 rats, where we have taken g to be 10 meters per square second, which is the acceleration due to gravity. That's all for question 2. We proceed with question 3. In question 3, which is a direct impact, where we have two spheres, A and B, and then sphere A is initiating the motion, and B is initially at rest. So we are given the initial velocity, as you can see on the slide, as 4 meters per second, which is before impact, and then B is at rest, as you can see here, and then at impact we have the impulse therefore exerted by A as resulting to B, Ga of A, and vice versa, we have the impulse exerted by B as resulting to A, we have G of B. So after impact, we then have their velocity, VA and VB. And remind ourselves that after impact, the both spheres move in direction to sphere A, as you can see on the slide after impact. So on the question task, we want to get the velocities of A and B after impact, and we comment on their result. So in that case, we apply the principle of conservation of linear momentum, which says that momentum before collision equal to momentum after collision. So we can have the momentum before, and then we have momentum after. Now replacing their value as data collection, we have 2 VA plus 8 VB. Now since B was stationary, its initial velocity is 0. So this gives us therefore as equation 1, VA plus 4 VB equal to 8. So we also apply the nails, that's from Newton's experimental law, where we have E, the coefficient of restitution, the velocity of VA minus VB over V over UA minus UB. We then have as equation 2, since B was stationary, negative VA plus VB equals to 2, give us as equation 2. So therefore, solving the simultaneous equation for 1 and 2, we then have VA equals to negative 4.5 meters per second, and VB 6.5 meters per second. So that gives us the velocity. So to comment, we then see that VA is negative, so the negative gives indicates the change in direction of VA completely. So again, in B, we have the magnitude of the impulse experienced by A due to the impact. So the magnitude of the impulse on A, we have MA into change in velocity, that's resulting to the impulse. We have VA minus UA. So having the distributive property, we can have MVA minus MUA, where MA is the mass of sphere A. So replacing their value, we then have negative 56.5. Therefore, the magnitude of the impulse becomes 56.5 kilogram meter per second. In C, we are to get the loss in kinetic energy due to the impact. We remind ourselves that the loss in KE is just the KE initial minus the KE final. So as you can see on the derived formula, so in that case we need to get the initial KE and the final KE. So on the initial KE we have as value MA, since there were two spheres, U square at A. Should not forget the half, which is the half mu square for sphere A. Then similarly for B, since B was stationary, so its own KE becomes 0 initially. So this gives us a total kinetic energy initial as 16 joules. So we then get the final kinetic energy, which is same half. Since it's final, we have m v square. So for the both spheres, we then have 32.5 joules by simplification. So therefore, our loss in K, we then have 48.5 joules. So that gives us, therefore, the total loss in kinetic energy. So again, we come back to question 4, which is under Hooke's law, where we have to get lambda. So we are given an elastic string AB of natural length 1 meter, and then in that case we want to get the modulus of elasticity lambda, and then we find the work done. We remind ourselves that from Hooke's law we have the tension given as lambda x squared on A. So our x here is the extension, our A is the original length of the string. And our original length of the string, which is 1 meter, and our extension we have 0.2, then give us as tension acting on the elastic string 0.2 lambda. We remind ourselves that T is mg, equals to mg, the mass which was 2 kilogram. So replacing it and solving the linear equation, we then have tension as 1000 Newton. Yeah. So in that case, from the work done, we then have lambda s squared on 2a. That's the total work done, but take note that we have at x2 and at x1. So at x2, we can see on the slide, we have 100, since they have a unique modulus of elasticity. So having the simplification done, we then have the total work done as 15.625 joules. So in that case, our found lambda will be 100 Newton, and our total work done becomes 15.625 joules. So in sub 2, that was sub 1, sub 2, we get the maximum velocity. So the maximum, we have the mass 1000 kilogram, moves along a straight horizontal road, that's under work done. And then on the figure, we have the mass pulled on the horizontal road, and the movement of acceleration, which is directed towards the force F, and force, which is the P on V. And then there is a resistance opposing the motion R. So there's always the weight, which is mg. Yeah. And then we remind ourselves that from Newton's second law, the sum of the external force is balanced by ma. So in that case, from since the pulling force is F, the force, we have F minus R equals to ma. But we remind ourselves that at maximum velocity, acceleration is 0. So in that case, as a new equation, we have P over V max minus R equals to 0. So having our collecting data, power which was 15 kilowatts, so we have 15,000 watts, over V max, our resistance was 5,000. So having our simplification done, we can have V max as 10 meters per second. That's for A. So that will give us the maximum speed of our car. In B, we get acceleration. So to get acceleration, maintaining the speed, so we come back to our reference equation, P on V minus R equals to ma. So maintaining V, we can have as equation this, as you can see. So from there, we can easily simplify, and solving and maintaining V, we have acceleration, which is the QAD, 50 minus 6V over V, which gives us as unit meters per square second, which is the proof on the question. In question 5, we have projectiles, where on the first task, we have to get the Cartesian equation of the trajectory of the particle P. So our P is projected from O on a horizontal plane at t equals to 0. So again, we have the initialized velocity 5i plus 5 g meters per second. So as you can see on the figure, we have the direction angle alpha to the horizontal, and we have the initialized velocity. When we resolve, we have 5 and then we have 5 for the other components. So again, to get our value, we need to first know the speed. So we have the magnitude of the velocity, which will give us 10 meters per second. And from Pythagoras theorem, Socrates, we have tan alpha, which is opposite over adjacent. So we have the change in the y over the change in x, give us as alpha the direction angle 60 degrees. So therefore, we can be able to get the trajectory equation of path, which is given to us as y equals to x tan alpha minus gx squared over 2u squared into 1 plus tan square alpha. So replacing our found value, we can have our trajectory equation by simplification. We have y equal to 3x minus x squared on 5. In B, we get the maximum height attained by P above the horizontal plane to O. So we remind ourselves that the maximum height, we have u square sine square alpha on 2g. So our found value, we have alpha, and then we have mu. So therefore, our maximum height by simplification, we have 15 on 4 meters as units. And lastly, we get the distance of P from O when t equals to 2 seconds. We remind ourselves that the distance with the magnitude of their corresponding displacement along the horizontal and along the vertical. So here we have x along the horizontal, ut equals theta. So replacing our value, which is 60 degrees as angle. So we have the horizontal as 10 meters. For the vertical, we have ut sine theta minus half gt square, which is as resulting from the equation of motion, s equals to ut minus half gt square. But our U, is represented as UY, which is the vertical displacement. And the vertical displacement will be U sine theta. So replacing our value, we then have 10 root 3 minus 20. So finally, the distance of P becomes the magnitude along the X and along the Y component. Give us as a decimal value 765.4 meters. In question 6, we have system of forces. In system of forces, here we are to get the point of intersection. So we have two forces, F1, F2, acting with different position vectors, R1, R2, respectively. I want to show that their line of action intersect, and we find the position vector of their point of intersection. So in that case, we remind ourselves that the line of action is given as L equals to, we have the position vector plus lambda F. So therefore we can build equation 1 for line 1 as this value. For line 2, we have the same. We have the position vector plus the scale, that's lambda, which is the scale constant, to which is parallel to. Therefore, solving simultaneously and outputting their different component I and j's, the intersects when L1 equals to L2. We have as 3 equations. For the I component, we have 1 minus lambda should be equals to negative for the other one. In line 2, we have same. For equation 2, we also have negative 1 plus 2 lambda should be equals to the other component in L2. So solving simultaneously, we have lambda equals to mu as 1. So substituting our lambda and mu in line 1 and line 2 gives that the intersect with a common position vector j plus 4k. In sub 2, we have kinematics, where we are to get the speed of the particle when t equals to 5. We remind ourselves that the acceleration of a particle is starting from rest. It has value as 10 on v meter per square second. So therefore, to have we can get the derived unit, which is dv on dt for the acceleration. When we make the calculus, we have v dv equals to 10 dt. So again, by linear integration on both sides, separating the variables as differential equation, we can have v squared on 2 equals to 10t by integration plus k, but k is the constant of the integral. So using the initial conditions, replacing, we clearly have k to be 0. Then substituting back in our original equation, we see that our v squared becomes 20t. So therefore, when t is 5 seconds, we can have v as 10 meters per second. That's for question 6. Question 7 is center of gravity, where we have a lamina composed with a right angle lamina, triangle lamina. So our lamina has 2 partitions. We have a square lamina and a right angle triangular lamina. So the first task is to get the distance centroid. But on the figure, we can have our different partitions of the laminas. We have PTRS and we have RTQ for the triangular lamina. So again, we don't have the distance RT. So we can purposely use Pythagoras theorem. So in that case, we have as value RT, which is the square root of 5a square minus 3a all that square. Give us as change distance 4a. That will help us to get the distance RT. So we first have the units lambda per unit area of the composed lamina. We then have the weights equals to a lambda. So in that case, from the table, we have the different partitions PTRS and we have RTQ. And since a known portion were removed from the lamina, we have the whole lamina as PQRS. Then the area, since it's a square lamina, we just have length times width 20 a square. Then for the right angle, which is half base times height, we then have 6 a square. Therefore, since none of them were removed, so we just have the sum as 26 a square. Now the weight is will be the lambda attached, since lambda was the weight per unit area. So we then have the weight as 20 a square, and for the PTRS, same for the RTQ and the whole composed lamina. Now the distance centroid, we have PS and PQ. We remind ourselves, coming back to the figure, the PS, here we have PS. So if we take the whole lamina center gravity here, so in that case, let's take this portion purposely. The distance it makes with PS is towards the x-axis. So the distance centroid will be given as x bar. And for PQ is totally vertical, so it goes with the y components. So the centroid incubated by PQ will be y bar. So the whole lamina has let me see, whole capital G1 into S bar y bar along the x for PS and y bar for PQ. So therefore we can see, coming back on the table, the distance now for PS will be x bar, for PQ we have y bar, as you can see on my circles. So now let's get the individual distances. So for PTRS, which is the square lamina, so since we have, coming back on the figure, the distance P, we have RS is 5A. So having it as 5A, it means that the division is equally distributed. So we have 5A on 2 and 5A on 2. So therefore, the distance that the square lamina will make with PS will be 5A on 2, as you can see here. Then for the right angle triangle, we remind ourselves that for a right angle triangle, the distance is always 1/3 from the base and 1/3 from the height. 1/3 from the height. So to know the distance covered by the right angle triangle with PS, we have as 6A. So if this is our portion, yeah, so we need PS. So it's from here to here, and we have from here right up to here. So we remind ourselves that from here to here it will be 1/3 from the base. So we then have 1/3 of 3A. So having 1/3 of 3A, we have just A. So since we have from here to here, which is A, then now adding now with the square distance from here to here, which is 5A, we have as total 6A, as you can see. So that gives us the column for PS. Now for PQ, we come back to the box diagram. PQ we have from here to here. Now we start with the square lamina. The square lamina PTRS goes down equally with 5A on 2. That's dividing the length from P to T. We have 5A on 2. So therefore, our PTRS, we then have here 5A, 2A. Now the PTRS give us as 2A. So again, we come back to the box. We get the distance RTQ. RTQ, which is this portion, the square lamina, will have as value 4A on 3. So we remind ourselves that we have PQ, which is this direction. It goes with 1/3 from the height. So 1/3 from the height, we have 1 on 3 into our total height RT is 4A, as you can see. So therefore, it will give us as value 4A on 3 on the table. So coming back on the table, we have 4A on 3. So this gives us our complete derived component. So therefore, taking moment at PS, since none of the portion were removed, we have the moment of the whole lamina equals the moment of the individual partitions. So you have the direction angle here towards G. So therefore, we have the weight times the distance. So the whole lamina starts, we have 26A square lambda x bar equals to 6A square into 6A. So solving it and simplifying, we have this linear equation. Finally, give us the distance centroid as 43 on 13A. Similarly for PQ, about PQ, we have this, that's P here, and then we have Q here. So we have the weight times the distances, so we have this direction. So simplifying, we have this linear equation. So finally, we have 24 on 13A. So this gives us the overall distance centroid along PQ and PS. In B, we get the angle, the tangential angle at the HPS with the vertical. So if it is hinged at S there, we then have, if it's held at S, we have the displacement along the vertical component. So therefore, our tangent angle from Socatoire opposite over adjacent. So we have x bar over 4A minus, we have x bar over 4A minus y bar. So therefore, replacing the values, we then have 43 on 28 as tangential angle held at the HPS. Lastly, in question 8, we have probabilities. The first task, we have two events, A and B, and we have to get P of B. But to get P of B, we remind ourselves here that the P of A union B was given. And the P of A union B, we have 7 on 10. 7 on 10. So therefore, we remind ourselves that we can use general event. So using general event, this one should be 7 on 10 actually. P of A union B. Yeah. And then we have P of so this one is not there. So actually, so This one is not there. So we then have from general event P of A union B equals to P of A plus P of B minus their intersection. But since we're given this value, probability of A intersection B prime, we need to come up with a derived unit. Let's come up with a derived unit. So we remind ourselves that if you have two sets, that's A and B, A, this is A, yeah? And then we have B. So A complement, we have these elements, and A complement intersection B is the same element. That's it here. And this is the intersection, A intersection B. And to know the element of B is the probability of B equals to the probability of this set plus the probability of this set. So from there, making this subject the formula and replacing in this value, we have this equation. So therefore, simplifying and replacing their units, we have the P of A union B equals to 2 over 5, where this should be P of B and not P of A. So again, we continue with sub 2. In sub 2, we are to get that's a tree diagram. We have to get we have a tree diagram we have here. At lunchtime, we have a man choose at random from 3 restaurants. You have X, Y, Z. So we have a tree diagram. So we have 3 restaurants, X, and we have Y, and we have Z. So we then have, you can choose either to go for lunch from the restaurant X, or it does not. That's L and L prime. And then we have the distributed probabilities equally, as you can see. We have this and for X and for Y and same for Z. So the first task is to find the probability that the man will have lunch. So having lunch, we don't know whether he can take from X restaurant, Y, or from Z. So by union, we have by OR, we have plus here and plus. So since the events are independent or true, we can see their distributed probability when it's taken across. So when I take it across here, we have multiplication, and here we have addition. So that's why here we can have this distributed operation. So therefore, our value for the launch probability will be 47 on 200. In B, we have the question says the man will not have lunch. So having the probability for lunch, you just mean 1 minus the probability. Having the probability for lunch, so to have the probability for him not to have lunch, you just take 1 minus the probability for him to go for lunch. So having that value, we can have 153 on 200. Lastly, we have the probability, conditional probability, y given L. That is y is chosen given that the man who have lunch. That's the probability an event had not yet occurred, given that an event already had occurred. So distributing the probability, we have the conditional event. So we have P of y intersection L over P of L. So since P of L was found already, so replacing the two values give us the probability for the man to choose y, given that he takes a lunch. So this gives us the whole board set for the questions. So hope to see you guys in our next videos, and I hope it was in use.